Hi everyone. Uh, in the last few lectures, we have been talking about Schmidt triggers. We discussed Schmidt triggers with symmetric and asymmetric threshold voltages, and we saw why we use Schmidt triggers in analog circuits. Okay, so in this lecture, I thought I'll discuss a very interesting problem. I think that appeared in GATE 2024. Okay, it was based on Schmidt triggers, and I thought I should explain that problem. It's a very simple one, but it's a good problem to solve. Okay, so if you guys recall in our first discussion, what I've shown here is just a symbolic representation of a Schmidt trigger. So this curve here shows the hysteresis. This picture here shows the hysteresis. So usually you will be feeding a sinusoidal signal or a ramp signal to a Schmidt trigger, and the output of the Schmidt trigger will be a perfect square wave output. Okay, so remember, a square wave output is a signal whose transitions from low to high values will be sudden. It will be instantaneous. Okay, it has to be instantaneous. That's one of the reasons why we use Schmidt triggers for, right? Schmidt triggers are essentially they convert a slowly varying signal to a signal with very sharp edges. Okay, so normally where do we use Schmidt triggers? I'm just going to repeat that point. I said, let's say we have you have a chip, a digital chip, which is soldered onto a printed circuit board, and to the printed circuit board, on the printed circuit board you have a connector. It can be an SMA connector. So if you don't know what SMA connector is, don't worry about it right now. Let's assume that you are feeding a clock signal to this point in the chip, in the board, in the printed circuit board. Then you'll have a copper routing that will route this clock signal into the chip. Okay, now usually these copper planes, depending on the frequency, if your frequency of the signal is very large, these copper planes, you can think about it like it'll act like an RLC circuit. Okay, so which means it'll act like a low pass filter, and it will filter out all the harmonics. So what happens if you take a periodic square wave and remove all its higher harmonics, right? You are eliminating all the high frequency sinusoids. So what you will be left with is a pure the fundamental sinusoid itself. So when the signal reaches the chip, when it enters the chip, the waveform will look like a sinusoid, or it can actually even look like a ramp waveform. Okay, if you think about it, a ramp signal and sinusoidal signals are not very different. I mean, there are obvious differences, but if you look at the observe a ramp signal or a sinusoid near the zero crossings, okay, if you observe them near the zero crossings, they both will look very similar. For a ramp signal, the slope of the signal remains constant, right? When your signal is increasing, the slope will remain constant as it goes from a low value to a high value. But for a sinusoid, the slope is maximum near the zero crossing, and as it reaches the peak, the highest value, the slope will go to zero. Okay, that's the big difference. But near the zero crossings, they both will look like similar waveforms. Now, what does a Schmidt trigger do is that it will convert this. I mean, for example, when we began our discussions with comparators, we said comparators are often used to convert these sinusoids, which are slowly varying signals, especially near the zero crossings, they are slowly varying, to square wave outputs with very fast edges. Okay, suddenly your output will change here. And these clocks, I mean these pulse signals at the output of your Schmidt trigger will normally be used as clock signal for your digital circuits. Okay, so what is of interest to us? What is of interest to us here is the zero crossing event, the time at which the sinusoid crosses zero versus the time at which the pulse signal has a rising edge event. Okay, because usually edge just matters to synchronous circuits or synchronous systems. Therefore, what is of interest is at what time does the input signal cross the zero, and at what time does my output signal cross the zero, right? The zero crossing event for a pulse signal is nothing but the rising or falling edges. So mainly, since it's a clock signal, it's a synchronous system, usually it will operate on one of the edges. So here I'm interested in the time at which the sinusoid crosses the zero, okay, and the time at which the clock signal crosses, the pulse signal crosses the zero. This information might be helpful. So this is something that is of interest for circuit designers who are especially dealing with Schmidt triggers or any sinusoid to square wave converters. So the problem in GATE 2024 was an interesting problem. It kind of gives you an understanding, how to estimate this rising edge to rising edge delay and all that. Okay, it's a very simple problem. Now that we have already discussed Schmidt triggers in great detail, it's a very, very simple problem. For most of you, if you have followed the last 4-5 lectures, it's a very trivial problem. The question given is this. It's a non-inverting Schmidt trigger circuit with a saturation voltage of plus minus 10 volts. Okay, Vsat is plus 10 volts, and it is given that a ramp signal, okay, ramp signal with a peak voltage of plus 2 and a negative peak of minus 2 volts. Okay, it's a symmetric ramp waveform is being fed as an input to this circuit. You are supposed to find out what kind of a waveform will come at the output of the circuit. So as I already said that it's a very, very simple circuit. So now that we have already analyzed non-inverting Schmidt triggers, the first step you'll have to compute is what are the low to high and high to low threshold voltages, right? So it's a non-inverting Schmidt trigger. So how does the characteristic of a non-inverting Schmidt trigger look like? So you'll have the output, the low to high voltage usually will be greater than the high to low voltage. So as you keep increasing your input, at some point it will cross the threshold voltage and it will reach plus Vsat from minus Vsat. Okay, and similarly at some point, as you keep decreasing your input voltage, at some point it will go to from plus Vsat, it will go to minus Vsat. Remember, it's a non-inverting Schmidt trigger. So I'm not going into details of that because we spent many lectures talking about them in the last few series of lectures. Okay, so now the first step is to find out what are the threshold voltages. The low to high threshold voltage is beta plus beta Vsat, and beta in this case is R1 by R2. So R1 by R2 times Vsat, and R1 by R2 is given as R1 is 10k, R2 is 100k. So 10 upon 100, it's 0.1. 0.1 times Vsat is 10, so it's 1 volt. So the low to high voltage is 1 volt. The high to low threshold voltage is minus 1 volt. Okay, you have 1 volt and minus 1 volt. So now you know the thresholds. That's it. You know the thresholds. You can now easily draw the output waveform. Okay, so keep in mind, anytime you are analyzing a Schmidt trigger, the first quick sanity check that you should do is look at the peak to peak output voltage of this signal. The peak to peak output is actually what? It is actually plus minus 2 volts. And what is your threshold voltages? The low to high and high to low threshold voltages, it is plus minus 1 volt. Because your signal's peak, right, it is exceeding both the high to low and low to high voltages. Yes, you can expect that the output of your Schmidt trigger will change as desired, meaning it will produce a signal which is changing its polarity. Otherwise, if your input signal peak is less than plus minus 1 volt, right, your output will either be at plus Vsat or it will be at minus Vsat. Okay, you will not see any changes in the output. So that's a quick sanity check. If you want to, you can do that. Now once you know that, you can just directly draw the threshold voltages. You have the waveform. Plus 1 is the low to high threshold, minus 1 is the high to low threshold. The moment your input signal reaches plus 1 volts, your output will go from minus Vsat to plus Vsat. Right? That directly follows from the graph. If you look at this graph, it will look like something like this. Okay, your output, when the moment it crosses plus 1 volts, it's from a negative voltage, it is reaching plus 1 volts, and then it crosses plus 1. At that point, your output goes from minus Vsat to plus Vsat. So your output will go from minus 10 volts to plus 10 volts when your input crosses 1 volt. Assuming the zero crossing happens at 0 seconds, what is the time at which the signal crosses 1 volt? Since it's a ramp signal, you can easily find that out. It's given the total time period is 8 microsecond. The waveform is symmetric. So the T/2, the 1/2 cycle will be 4 microseconds. And assuming again the waveform here is symmetric here, the 1/4 of a clock cycle will be 2 microseconds. Now in 2 microseconds, the signal reaches 2 volts. So how long will it take to reach 1 volt? It will just take 1 microsecond. That's it. Okay, so the time at which the zero crossing will occur will be 1 microsecond. So the rising edge to rising edge difference. Okay, so you can say that the delay between the input waveform and the output waveform is 1 microsecond. Okay, the event of interest is the rising edge, the point where the signal crosses 0 volts at the input, and versus the event point at which the output crosses the 0 volts in the output. Okay, at the output, and that happens to be at 1 microsecond, and for the input it is at 0 microseconds. Okay, see, remember guys, when you analyze Schmidt triggers and circuits like that, you can always analyze it from t equal to 0. What I have performed now, this analysis is what we call a steady state analysis. Okay, in the steady state, this is what you should expect, right? You can just draw the steady state waveform by looking at the transfer characteristics. Just look at the point where your output crosses plus 1 volts. At that point, for a non-inverting Schmidt trigger, your output will go from minus Vsat to plus Vsat. It will directly go from minus 10 volts to plus 10 volts. Okay, Vsat is 10 volts here. That's it. So on that time, the time at which it crosses is the time at which the output sees a rising edge, is the time at which your input waveform crosses the threshold voltage, and that happens to be 1 microsecond. And if I remember right, I remember seeing the solutions for that question. The circuit was a bit more complicated. It had some other, I think, an integrator after this, following this. Okay, and if you look at the choice of questions, there were 4 choices. It's a multiple choice question. There was only one choice which said the delay between the input and output was 1 microsecond. Okay, so naturally you didn't even have to look at the other questions. You could just pick that choice as the answer. Okay, just bear in mind, exams like GATE, these exams are just supposed to test your basics. Okay, they're just the minimum basics that you should know. So that's what they test you. So they will never ask extremely complex questions, will not be there in exams like GATE. Okay, they'll just test your basics. Have you understood the way the circuits has to be understood? That's enough. If you have understood that way, you should be able to answer it very easily. Okay, usually I think if you are expecting very complex questions, you don't see them in entrance exams. Okay, usually you don't, because there is a time limit. Okay, you have to answer those questions very quickly, so you don't have much time for that. So usually we don't ask. I'm using the word we because I was also a teacher, and when I conduct exams for the course exams, I don't set very tough question papers. I set tough question papers for a select group of students who work with me. I usually pick 4 or 5 students to work with me, and for those 4 to 5 students I would set very tough papers, because these guys are going to become engineers. I'm going to know that, okay, these 4 to 5 guys are going to become serious analog or RF engineers, so therefore I can test them to any level of difficulty. But when I'm taking an exam for an average class of say 200 to 400 students, the exam papers will be just not very tough, reasonably tough, so that I can grade properly, because so that you will have to avoid A grades and all that. But on an average, the question papers will be very simple. You should be able to answer them very quickly within that half an hour or 1 hour of duration for the test. You should be able to answer those questions. Okay, so that's what I'm saying. And in that choice of 4 choices, there was only one choice which had this. I remember seeing this sometime, I think it's more than a year now. So there was only one choice which had 1 microsecond delay, and you could just simply pick that choice as the answer. Okay, so if you are interested, I'll just quickly say the question in fact contained something more than this. What it had was, it had one a Schmidt trigger followed by an integrator. I think it was an inductor based integrator. Okay, so remember guys, this is not a practical circuit. It's just an exam question given to GATE. We don't build integrators using inductors. Okay, so the question was, I think this was node voltage VO1 and this was node voltage VO2, and you're supposed to find out what is the what they didn't even ask you to find the exact waveform at the output. The choices were VO1 and VI. There was a delay of 1 microsecond, 0 microsecond, I think 2 microseconds and 2 microseconds, something like that. Okay, and what kind of a output waveform should be there at this integrator's output? That was the question. Just give me a few more lectures. In fact, I haven't completed my series of lectures on pulse response of integrators and differentiators. I just finished step response of integrators and differentiators in great detail. If you just extend that, you can easily do pulse response. Okay, what happens if you feed pulses or periodic signals to integrators and differentiators, how they behave? I'll cover them in great detail. When I do that, at that point I'll talk in great detail about this circuit. Okay, but right now I'll just quickly tell you guys how to analyze this. So here I know the output is a pulse signal. The output here is a periodic square wave output, and the duty cycle is 50%. If you guys observe this waveform here, the input waveform has some kind of symmetry. It's a periodic signal. The threshold voltage is a symmetric, Schmidt triggered with symmetric threshold voltages. Therefore, the duty cycle will also be 50%. I mean, you can see the on time will be between this 1 volt and this -1 volt. Okay, when your output goes lower than -1, that's when when your input goes lower than -1, your output will go to -Vsat. So that's your high to low transition point. So therefore, if you compute its on time, your on time will be, it went high at 1 microsecond, then it will go low at 4 plus 1 5 microseconds. Okay, so the total time period for which it is on is from 1 micro to 5 micro, which is 4 microseconds, right? Which is half the time period. So what you have here is a pulse signal with 50% duty cycle, which goes from -10 volts to +10 volts, which is being fed to an integrator. So remember, anytime I feed a square wave output with 0 DC average to an integrator, you should expect to see a triangular waveform at the output. Okay, you should expect to see a triangular waveform, but you have to bear some points in mind. If this was an ideal integrator, you will see a triangular output. But if this integrator has some limits, if there is a saturation limit, let's assume it's +10 volts and -10 volts, then what you have to do is that you have to very quickly you will have to compute the integrator's time constant. Let the integrator time constant be tau, which is given by L upon R. I don't remember the exact time constant value, so I'll leave that aside. Okay, the time constant is L upon R, and the slope of the slope of the wave. See, anytime your output is a ramp, the unique characteristic of a ramp is its slope. Okay, once you know the slope and time period, you can compute what the peak values are. Okay, if that what I said just now doesn't make quick sense, you can verify it. Just think for a moment. If you have a ramp waveform like this, I can either give you the peak voltages -V peak and the time period together. Then you can compute the slope. You can compute the slope of this waveform. Okay, on the positive half cycle, the slope will be positive. Negative half, the other half cycle, it will be negative. The slope will be negative in this half cycle. It will be positive in this half cycle. Okay, so if I give you the slope and the time period, you can automatically compute the peak. How do you do that? Multiply your slope by T/2, half cycle, right? Multiply your slope by T/2. That will tell you the peak to peak voltage. What is the voltage it had? I mean, what was the net change in the voltage from the the minimum voltage to the maximum voltage? Okay, yes, slope times T/2 will tell you that. Now, what you need to do when you're analyzing an integrator circuit, quickly do this computation. The peak voltage is 10 volts. Okay, the slope for an integrator circuit is simply the peak voltage. For example, if you apply a constant voltage to an integrator, 10 divided by tau, that's your slope. Okay, by the integrator's time constant will be your slope. Multiply that by T/2. If this is greater than ±10, that's the peak to peak change in the voltage. If this is greater than 20 volts, you should expect that your waveform will saturate like this. Okay, so what you would see is a trapezoidal waveform. You will not see a ramp waveform. What you will end up seeing is a trapezoidal waveform. So you don't even have to do a proper analysis of the circuit. Just do this analysis. Quickly do this computation. Find its time constant. Then the peak voltage divided by tau, that's your slope. Multiply it by T/2, that's your time period. That will tell you what is the total peak to peak change from the negative to the positive value. The negative peak to the positive peak value. if that happens to be greater than, see, in an op-amp with a saturating limits of minus 10 and plus 10 volts, the total change in the output possible is from minus 10 to plus 10, right? Your output cannot go from, the total maximum change in the output voltage is 20 volts. Okay, it can go from minus 10 to plus 10. That's the maximum change. So if this happens to be greater than 20 volts, then you obviously know that the output would have saturated. So then the output waveform will look like a trapezoidal waveform. That's it. So with this information, you can answer this question. So first you'll have to quickly find out the first part of the circuit is a non-inverting Schmidt trigger. And for a non-inverting Schmidt trigger, by now you know how to analyze it. Quickly you can compute the zero crossing to zero crossing time difference, which happens to be 1 microsecond here. So you can say that the output here will be a square waveform and a delay with a delay of 1 microsecond from input to the output, the first stage output. And the final output, the output of an integrator will be, it will not be a ramp waveform, it will actually be, it will not be a triangular or a ramp waveform. In fact, it will be a trapezoidal waveform. Okay, with it's a triangular waveform with saturated outputs, or I can say a clipped triangular waveform. Okay, a ramp waveform which is clipped at its peaks. Okay, or it's a trapezoidal waveform. That's it. So using these two information, you can simply answer this question. It should not take you more than 5 minutes. Okay, if you already know non-inverting Schmidt trigger, you already understand how an integrator works, then this computation should be enough to tell you whether it's a triangular waveform or a trapezoidal waveform. Then you're done with it. Okay, if you did not exactly follow how did I say this, just wait for a few more lectures. I'll talk in great detail about integrators and differentiators, pulse response of integrators and differentiators. I'll answer the question there. Okay, thank you.